Hello everyone, my name is Chris Ferrier, and today I'll be presenting to you a little bit about the heat and mass project that I chose to do for assignment B. So this all started when I was back in my hometown of Shreveport, and I was looking for something to do. And if you've ever been to Shreveport, there's not a lot to do, so I went to the Goodwill to see what I could pick up. And I'm a pretty passionate cook, so I thought to myself, what do I not have in the kitchen yet? And I saw this wok that just landed right in front of me, and I said, I have to buy it. It's a pain to clean and it's a pain to keep around, but I've enjoyed using it so far. The problem with this is that I have been told that the reason people use woks for stir fry or other really high heat dishes is because it conducts heat very well. So, uh, using my heat and mass knowledge, presumably that means that it has very high thermal conductivity, meaning that it doesn't hold heat very well, but it will conduct heat very well, which is what you're really looking for in something like a stir fry or another dish that takes a lot of high heat like that to really get the flavor that you're looking for. So my project was to find the thermal conductivity of this wok that I purchased from Goodwill. Generally, woks are made of carbon steel, but they've kind of been shifting towards like the cheaper ones or the knockoff ones to be stainless steel. It does appear, I don't know if the camera can pick it up, that this one has a finish on it. So obviously that'll affect the conductivity a little bit. It shouldn't very much. Real woks just come as seasoned carbon steel, and you don't have this sort of shiny finish on it. I think it's probably Teflon or probably something cheaper than that. So yeah, I'll just get into the presentation about how I actually went around and calculated the thermal conductivity and determined the material that we're looking at here. All right, so like I said, my name is Chris Ferrier. This was for assignment B for heat and mass transfer taught by Dr. Lawrence. And for the fancy title, it was determination of a wok material based on the thermal conductivity that I performed an experiment to figure out. So let's go over a little bit of the purpose here. You can see that basically just restating what I said, it was bought from Goodwill. Obviously, I don't know the material. It was basically brand new from what I could see in terms of whenever I bought it. Like I said, most woks are made of carbon steel, but it could be another type of steel. And carbon steel has that highest thermal conductivity, which makes it great for cooking stir fry or other high heat dishes. And you can actually see on the right here, this is pulled from Engineering Toolbox, basically just a description of the thermal conductivity of different common cooking materials. So you can see down here with the stainless steel, you end up with a thermal conductivity of 14.4, and that's not even accounting for the coating that gets put on a lot of like Teflon type pans. So it would likely even go down even further. You're probably looking at something around 12 watts per meter Kelvin, which doesn't really give you that type of high heat. A lot of the heat is going to be lost to convection before it's really transferred into whatever you're cooking. But you can see as you go into the carbon steel that the thermal conductivity goes up pretty drastically. With 1.5% carbon here, you're looking at around 33 watts per meter Kelvin. And then at 0.5% carbon, you're looking at around 54 watts per meter Kelvin. So that's the really high heat. You're basically, there's not much heat being lost to the material itself. So you're getting a lot of heat pumped into whatever you're trying to cook. So I designed an experiment to figure out the thermal conductivity of this wok. And the first step was that I had to boil a quarter of a cup of water that was at room temperature initially, or 298 Kelvin, to determine the heat transfer rate. And I'll go over whenever I do the calculations a little bit more in depth on how I actually went about that. So you can see a picture of the water boiling here in the wok. I also had to measure the thickness of the wok. Typically, woks are made out of 14 gauge steel, which is a 1/16 of an inch, and you can see that reflected in the picture here. They're also, they prefer this thin material just to go back to the heat transfer as well. And then finally, I had to measure the temperature of the wok and the burner. um, to determine that thermal conductivity using Fourier's law. So the first thing we had to do before we could get to the thermal conductivity calculation is we actually had to calculate the heat transfer rate. Um, basic thermodynamics tells us that there are two things that go into a boiling water from room temperature, right? So if we started out at 76 degrees Fahrenheit and we end up at the boiling point of water, we're going from 76 to 212. And that's just simple Q equals MCP delta T, where you're taking the mass of the water, and that was calculated using the density of water at room temperature, times the volume of a quarter of a cup, and you end up around with 60 grams of water. And then you multiply that by the specific heat of water, which is well known, and the temperature that you're raising it to. So you can see that we expend about 18 kilojoules in sensible heating, and that's getting it from 76 to 212 degrees Fahrenheit. Once it's reached the 212 degrees Fahrenheit, we have to vaporize it. And the reason that I chose vaporization as a sort of metric for how long it was going to take or how much heat we were pumping into the system is just because it's easily visible. So obviously you can see when the water is there or not there anymore. So basically what I did was I poured the quarter of a cup of water into the wok and I measured how much time it took for it to completely evaporate. So this gets us into the latent heat of vaporization here. You can see that the latent heat of vaporization is calculated by taking that same mass of water and multiplying it by the delta H of vaporization, or latent heat of vaporization. And that's 2.26 kilojoules per gram water. And you end up with around 134 kilojoules expended on evaporating the water, which is considerably more than the sensible heat. And that makes sense just because it's all being pumped into the phase change. So now we can calculate the total amount of heat that it took to both raise the water to the boiling point as well as evaporate it. And we end up with around 152 kilojoules needed to do that. And from that number, we can actually calculate the heat transfer rate of the burner, and that ends up at around 0.9 kilojoules a second. So now that we have all this information, we can actually go into the assumptions that are behind the thermal conductivity calculation. The first is that all heat is transferred through conduction. Obviously, this is not true. We're not operating in a vacuum. There is air flowing over the wok, so there will be some convective heat loss. But for the simplicity of calculation, as well as just the fact that it will most likely be negligible, I assume that there would be no convective heat loss to make the calculation a little bit easier. We also assume that the heat transfer is steady state. That means that the heat transfer rate is not changing over time, and that the wok is of uniform thickness on the base. So the base is the part that's actually contacting the burner. That's where the conduction is occurring. And we assume that there's uniform thickness on the base so that that part of Fourier's law can be satisfied. We also assume the temperature of the burner and the wok remain constant. So on the left here, you can see a diagram that represents the system that we're looking at here. The burner temperature came out to be 580 degrees Kelvin, and the wok came out to be 577 Kelvin. And just looking at this up front, we already know that our thermal conductivity is going to be pretty high because our temperatures are so close. So if our thermal conductivity was low, we would see a greater temperature difference across that length there. And you can see that the length, like I stated previously, comes out to be 1/16 of an inch, and that converts to 1.6 millimeters. And we can actually dive into the calculation now. So here you can see Ferrier's law written out. So at the top there, you have the heat transfer rate equals the thermal conductivity. That's that K variable times the surface area on the bottom of the wok times delta T over delta X. And you can see what that looks like translated into our variables, where the delta T is the temperature of the wok minus the temperature of the burner. And you can think of the K as sort of the resistance in between. Plugging in the values that we measured or calculated, we can come out and see that our thermal conductivity comes to be around 27 watts per meter Kelvin. And now we can interpret this to figure out what type of material we most likely had. So bringing back the table from the second slide, you can see that at carbon steel up here with a 0.5% carbon content, we have a thermal conductivity of 54, and the difference for that is 66.4% compared to our experimental value of thermal conductivity here. For the 1.5% carbon, we're looking at around 19.7%, and that's actually the closest. When you get down to the stainless steel, once again, we see a very large percent difference. So most likely, the pan is a carbon steel with 1.5% carbon content, and knowing that, we can be satisfied that our wok is a real wok and will do the things that we needed to do. So that's all I have for you today. I hope you enjoyed the video and keep on cooking.